Okay, the masked professor is on the air once more. So, and of course, this is computer-aided manufacturing. And let me jump to where we were last time, utilization. Utilization, that is the proportion of time that our resource is used relative to the time available in the definition of plant capacity. All right, they're using the formula utilization equals workload divided by production capacity, and certainly that's a workable definition. It's the usual way that we would measure percentage of efficiency. Now, often in production, we find that we have bottlenecks. So, often in a job shop, a batch production, assembly line, everything has to be processed sequentially through more than one workstation. So if our factory has n workstation types, let the subscript I identify the stations I equals 1, 2, all the way through n. If each station has one or more server, let SI denote the number of servers at station I. We have P part styles processed through the factory, so J denotes the part styles, J equals 1, 2, etc. up to P. So when we talk about part mix or product mix, it refers to our proportions of part or product styles. So let Pj, lowercase pj, denote the relative proportion of parts style J processed through the factory. So the summation from J equals 1 to capital P, the number of part styles, of our proportion of parts J equals 1.0. In other words, 100%. Each part style J goes through a certain sequence of stations, and that may be different than the stations that the other part styles are processed through. Again, I'm always an advocate of mixed model processing, so that we work on faster changeovers to give ourselves more flexibility. If several part styles visit the same stations, then the processes are probably different. So TSU and time of setup and cycle time are going to be different. The bottleneck model derives its name from the fact that the output of the production facility has an upper limit that's determined by the part or product mix values. Pardon me. Have to get some hard candy out. the output of our production facility has an upper limit determined by the part or product mix values and how fast they can go through the slowest workstation. So to determine the output limit, a weighted average workload is calculated for each station, where we say the workload of station I equals the summation from j equals 1 to capital P of lowercase pj, the proportional part mix, times the time for that proportional mix to be processed at I j. All right, so our bottleneck is the station with the highest workload per server. Okay, and often, if, for example, we use the theory of constraints, what we do is we look at that highest workload per server as our constraint on the whole system, and if we are having trouble keeping up with demand, we look for ways that we can lower that constraint, make that workstation that more efficient. So let workload star and S star equal the workload and number of servers respectively for the bottleneck station. Then our maximum production rate of all part or product styles is determined as the ratio production rate star equals server star divided by workload star. Maximum production rates for our individual part and product styles is determined by our production rate of J star equals the proportion of part style J times the production rate star. So our utilization of every server at workstation I is the proportion of time that its servers are working and not idle, and we compute that as U of I equals workload of I divided by servers of I times our production rate star. So our utilization of the factory is a weighted average of all the server utilizations. So U bar equals the denominator summation of I equals 1 to N of our number of servers I times the utilization I divided by the summation from I equals 1 to N of our servers. All right, so that brings us to our manufacturing lead time. So this is the total time required to process a given part or product through the plant, including any time for delays, material handling, queues before machines, etc. So that manufacturing lead time of J equals the summation from I equals 1 to NOJ of the time for setup of workstation I part style J plus the queue before the queue of items, part styles J times the cycle time at workstation I for part style J, plus the time for the number of operations at I for part style J. Oh, bloody hell. All right, and down here you see manufacturing lead time, MLT, J equals the part or product J, I equals operation I. In the operations sequence for the part or product J, NO is the number of operations, TSU is setup time, Q is batch quantity, TC is cycle time per part, and T of NO is non-operation time. Non-operation time. Weird. Of course, as a lean advocate, I would say that the batch size should always be 1, thus making our middle term in this equation the smallest possible. All right, so our work in process, that is the quantity of parts or products currently located in the factory that either are being processed or in between processing operations. So our work in progress, WIP, equals the production rate, star, times the manufacturing lead time. Right? You'll notice that our production rate, star, is defined as the hourly plant production rate. All right, well, of course, we know that in industrial engineering, the two things that we should always keep an eye on are time and cost. And there's an extent to which one can be transformed into the other. So our major categories for our manufacturing costs, first of all, are fixed cost. The fixed costs remain constant no matter what our output level is. So that is the cost of owning the machine, the cost of owning the facility, insurance, custodial staff, overhead staff, etc. Our variable costs vary in proportion to our production output level. So, for example, the more we produce, the more material we have to buy, and so that is a variable cost. When we add our fixed and variable costs, our total cost is going to be equal to the fixed cost plus the variable cost times the quantity. And they're defining it as TC is total costs, FC is fixed costs, VC is variable costs, and Q as output level or quantity. All right, one thing that we discover is that there is we can use graphic methods to take a look at what we would pay at different levels of production. And this is one method that we use to possibly, as in the case of this diagram, to decide whether or not we should automate a process. So you'll notice here Method 1 is the manual method. The fixed cost is low, and of course it varies with production, right? And it goes in more or less straight line. Whereas method 2 is our automated production. It has a higher fixed cost but a lower variable cost based on most likely the lower variable cost is the result of less manual labor having to go into the production. There will always be some kind of break-even point like this when we look at this kind of situation. Now, of course, we need to always be careful to remember that we don't automate just because it's cool or it's the latest thing. It's always an economic decision. If we can't justify automating for economic reasons, then we should never do it. All right, so an alternate classification of our manufacturing cost is when we say direct labor, which is the wages and benefits that we pay to workers, materials, the cost of our raw materials, and overhead. And that's all the other expenses associated with running our manufacturing. Also, that is sometimes called indirect, right? So that becomes our factory overhead and our corporate overhead. All right, so the typical manufacturing cost at J. Black, that sounds familiar, but I can't remember what that company does. You have the manufacturing cost at 40%, engineering cost another 15%, research and development 5%, administration, sales, marketing, all the administrative overhead type costs at 25%, and the profit at 15%. They break the manufacturing costs down further to the direct labor being 12%, the plant, machinery, depreciation, energy at 26%, although I would love to see that broken down further. The indirect labor at 12%, and then parts and materials at 50%. I would say this is pretty typical of the kind of calculations here. And of course it's simplified a bit for this particular diagram. All right. So our factory overhead rate, in other words, the percentage of factory overhead rate equals the factory overhead cost divided by the direct labor cost. Corporate overhead rate, the corporate overhead rate equals the corporate overhead cost divided by the direct labor cost. Now, this is one way of figuring out what the overhead rate is. Another way that I've seen used is to calculate how much is the overhead per square foot on the factory floor, so that we can calculate by the size of a shop or an assembly line what the total overhead rate is for that particular shop or assembly line. All right, so the cost of our equipment usage. The hourly cost for our worker machine system, where C sub O is our hourly rate, CL is our labor rate in dollars per hour. Our factory overhead rate for labor, our machine rate in dollars per hour, and our factory overhead rate for machines. All right, so C sub O equals our cost of our labor rate times 1 plus the factory overhead rate for labor plus the cost of the machine in dollars per hour times 1 plus the factory overhead rate for machines. All right, easy enough. Now, don't get lost in all of these. Make yourself a little cheat sheet to be able to refer to when you're doing problems for this. All right, so the cost of a manufactured part, that's going to be the sum of production cost, material cost, and tooling cost. So the cost for each unit operation is the total cost for operation I times the time for that proportionate part at operation I plus the cycle time cost at operation I. Our total unit cost is going to be the sum of the unit costs and the material cost. So the cost per piece, CPC, equals the cost of the machine, or excuse me, cost of material. They should have used a different symbol to differentiate that. Plus the summation of the cost rate for to perform a unit operation times the production time for operation I plus the tooling cost for operation I, where again CPC is cost per piece and CM is the cost of starting material. Okay, and they want to solemnly remind you that this material is copyright under United States copyright laws, so there. All right, that takes us through our manufacturing metrics and economics. These are kind of important calculations to make. We have to have a handle on whether we're making money or not because that is going to drive decisions about, hey, we should stop making this product or update it so that we can get more money out of it, or make it more efficient to make more product, to make more profit. So that we know that our company is going to be able to continue in business, right? Obviously, a very important thing. All right, let's save this as a PDF file. Sure, why not? Okay, all of these files will be saved on the computer as PDF files so that you can download those for studying purposes. Now, none of this information is anything that's different from what is in the book. The information that's different than what is in the book is what is my commentary on the slideshow as we go along. All right, so I am going to go ahead and close that and open Chapter 4, where we are going to have the introduction to automation. And you know what, on Tuesday I'll go ahead and run some of the calculations from Chapter 3. I would do that today, but I haven't really set up for that today. And I have other excuses. Please write if you need those. All right, so Chapter 4 is an introduction to automation. All right, so we'll talk about what are the elements of an automated system, what are advanced automation functions, levels of automation and artificial intelligence. All right, so you remember this diagram from, oh gosh, now I've forgotten if it's, I believe it's Chapter 2 of this book, where we talk about the enterprise level, the factory level, and bringing in automation and control technologies. All right, so automation, when we define that, is the technology by which a process or procedure is accomplished without human assistance. Although I say, who made those machines that automate? All right, the basic elements of an automated system. First of all, we have to have power. Power accomplishes the process and operates the automated system. We have to have a program of instructions to direct the process. But as I brought up during our initial lecture, that program of instructions doesn't have to be from a computer as such. It's been accomplished in different ways at different times, running a tape through the system with holes punched in it that tell the machine what to do, the Jacquard system with a series of little boards, etc. And all of that works with the control system, which actuates those instructions. All right, so the elements of an automated system, well, we have to have power to run the system. That doesn't mean it has to be electricity. It could be pneumatic power or hydraulic power or mechanical power that's delivered some other way. For example, in factories around the turn of the 20th century, it was very common for machines to be run off a series of belts that drove the machines. That power goes into everything, and it drives the program of instructions, which in turn feeds into the control system. The control system controls the process and gets feedback from the process, and those allow it to perform its job, and then we have output from the process, which is our product. All right, so the power that we have for the automated process, first of all, there's the power for the process. It drives the process, loads and unloads the work unit, and provides transportation between operations. Now, the power doesn't necessarily have to do anything except drive the process. We may have humans loading and unloading the unit and transporting the product or the work in process between the operations. Power for automation, we have a controller unit. The power actuates control signals, and there's data acquisition and information processing, right? We have to have that feedback from the process. Electricity is our principal power source these days. While there are still units that use hydraulic or pneumatic power or some other kind of mechanical power, electricity is so cheap and easy to use that usually it is the power source. We can convert it to other forms: mechanical power, thermal, light, the pneumatic or hydraulic power that we might use. Very low-level power can be used for signal transmission, data processing, and communication. Right? You think about the USB port in your computer, right? That runs on 5 volts. And you can transfer a lot of data back and forth at that very low power. We can store electricity in batteries. You can also store it using mechanical power or other means, but usually if we store it, we do it with batteries. All right, so our program of instructions, we have a set of commands that is specifying the sequence of steps in the work cycle and the details of each step. So we might have what we call a numerically controlled part program. Numerically controlled, at this point, usually refers to some kind of computer control. So at each step, there are going to be activities involving changes in the process parameters. So that might be a temperature setting of a furnace, the axis position in a positioning system, motor on or off, the tools that a CNC machine might use. You might have a CNC machine that has multiple heads, and the tools are being changed out to accomplish different operations during the process is being completed. All right, so decision making in our work cycle, we might have different levels of automation, right? The first is operator interaction, right? You go to the ATM machine, you don't just let it say, you know what, I'm assessing you and I think you need $400. No, we do different things. That is all in accordance with our input at the ATM machine. Different part or product styles processed by the system. That may need a human to say, hey, execute program 1 or program 5 or whatever. The example they give is robots welding together cars. That is a huge use of automation, and it makes total sense because, of course, with welding you need to protect your eyes, your body from sparks, whereas if a robot is doing it, the robot has no eyes to be hurt. The little welding dots we assume do not hurt the robots, so we're in great shape there. And we might have variations in our work units that we put in. They give an excellent example here. You might need additional machining if you have an oversized casting. In other words, when they cast it, it didn't perfectly cast like it usually does. It's a little larger than usual. If we don't interrupt the cycle, the machine will try and do it for the regular size, and you might break tools and have other problems. All right. So, when we talk about these programs, usually we call them CNC programs. We're going to have certain things that are going to be existing in them. One of them is going to be the number of steps in the work cycle. Right? Does it take 5 steps to accomplish this operation? Does it take 50 steps to accomplish this operation? There may be manual participation in the work cycle in that people have to load and unload the work parts, right? So usually when that happens, the machine signals that it's done, the worker goes, they unload the finished piece, they put in the unfinished piece to be worked on, close the door, punch the button to say start. What are the process parameters? How many do we have to control? That is going to make a big difference, obviously. How many tools do we use? how many parts of the part have to be shaped to make the part into the final part. Variations in the part or the product styles. As I said, you may have parts that are very subtly different from each other that are all run on the same automated system. So you put in the part and you punch up the correct program for that part, which may only very slightly be different from the program before or the program after. And we may have variations in our starting work units where we have to adjust the parameters to compensate for those differences. For example, the example from the last, boy, can I use example more? The example that we saw previously of a slightly oversized casting, for example. We might have a special program for that, because to assume that we need to program for the oversized casting and then let it shape, that would waste time and energy compared to when the casting is the correct size, right? So we might have a special program, or we might have some way of adding a little baby bit of programming to that program before it starts. All right, so when we talk about control systems, we have two types. One is a closed loop feedback type control system. In that case, it's a system in which the output variable is compared with the input parameter, and any difference between the two is used to drive the output into agreement with the input. If we have a system like that, we may be able to write a program that would take into account that oversized casting problem that I was talking about. In an open loop control system, it operates and does not have a feedback loop. It's simpler and less expensive, but there is a risk that things will go wrong and the machine won't realize it and be able to stop itself. The kind of automation that we talk about in lean production class. All right, so we have a feedback type control system here. We have our input parameter, length, diameter, shape of a particular feature, whatever. We have the controller, we have the actuator into the process, and we are feeding back on that output variable so that the controller knows if something is going wrong. If we don't have that, we just have the input parameter in an open loop system, the controller into the actuator, into the process, and we just have the output variable. If we don't have that kind of feedback, we probably have some kind of quality control check after this process. All right, so here we have a one-axis position control system where we have a lead screw that is driven by a direct current servo motor and uses an optical encoder as the feedback sensor. So the X value is fed into the controller. It gives the motor input. The motor drives that lead screw that's driving the work table. Maybe this is some kind of milling operation or cutting operation. The optical encoder is reading where the work table is and sends a feedback signal to the controller if something is going wrong or the work table has moved to where the machine is done. All right, so when do we use an open loop control system? Well, I actually have used lathes where you could set it so that the feed screw would operate the machine in different dimensions, but it was a very old machine, very simplistic, so I actually was the feedback sensor and would watch, and when it got to a certain point, I would stop the operation. So, when do we use open loop? When the actions performed by the control system are simple, right? So on the lathe I was operating, it would just feed down the length of the part that I was machining. The actuating function is very reliable. We definitely want reliable processes. Any reaction forces opposing the actuation are small enough that we're not going to have an effect on the actuation. If the conditions don't apply, these three conditions, then we need closed loop control so that we're getting feedback and the machine can stop itself if a problem is happening. All right, so advanced automation functions are things like safety monitoring, maintenance and repair diagnostics, and error detection and recovery. So, safety monitoring is just what it sounds like. We use sensors to track the system's operation and identify if there are conditions that are unsafe or could be potentially unsafe. Reasons for safety monitoring to protect workers and equipment. Okay, well, that seems a bit simplistic, but it's a good thing. The old laboratory maxim goes, experience gained is proportional to amount of equipment ruined. Well, you know what? If we can possibly avoid it, we don't want to ruin equipment. I have ruined my share in my day, but I would just as soon not ruin any more. All right, so what are the possible responses if we have a safety problem? One could be a complete stoppage of the system. Just have the machine stop the system and signal it needs help, there's a problem. Sound an alarm. reduce the operating speed of the process, or take corrective action to recover from the safety violation. Now, of course, that is the highest level of safety monitoring, and that requires a very sophisticated machine, except for the most simple operations. All right, so what maintenance and repair diagnostics can the machines do? Well, first of all, there's just status monitoring. It keeps monitoring and it's recording the status of key sensory input and the parameters during the system operation. Right? That could be a real-time thing where an operator is alerted if it seems like they're getting outside the parameters, or it could be a thing where we go back and review the record and say, well, wait a minute, over here we had a potential problem and we need to look into why that happened. Failure diagnostics only pop up if we have a malfunction. When we have a failure diagnostic, we can analyze the record and identify the cause of the malfunction. Now, often we use things like control charts to even monitor when we got close to a problem and try to figure out what happened there, so that we actually don't go to the malfunction place. Now, some machines are so sophisticated that they actually will recommend the repair procedure. So when we have that, that can be shot straight to the maintenance crew so that they know what needs to be done to repair the machine. Thus, it's not a thing of, okay, we know there's something wrong with this machine. What is it? Go through all the various troubleshooting guides. No, the machine has already told you. And the sophistication of these kinds of programs is getting very large. For example, the CH-47 helicopter, a workhorse in the Army since the late 1950s, is still being manufactured today, right? They haven't come up really with a better design than that. But now the design is much more sophisticated because they put all kinds of sensors in that will not only be diagnosing the problem, it sends by radio the recommended repair procedures and maintenance procedures back to the base while the aircraft is flying back. All right, error detection and recovery. Well, this is the kind of automation we talk about in lean production, where a machine needs to at least be able to stop itself if it starts making an error. So when we talk about the functions of error detection, we're going to use the system sensors to detect if there's a malfunction or any deviation from the process that might be a problem. It's got to correctly interpret what that sensor is saying and it has to be able to classify the error. When we talk about error recovery, some strategies we might use, we might make adjustments at the end of the work cycle of the machine. Maybe we make adjustments during the current work cycle of the machine. We might stop the process so that we can invoke some kind of corrective action. Again, might just stop the process and call for help. So the different levels of automation, well, first of all, there's the device level. Actuators, sensors, any kind of hardware component that gives you an individual control loop for the next level. It can be at the machine level, where CNC machine tools, other equipment like that, industrial robots, material handling equipment, is able to operate on its own, basically without supervision, except if there's a problem or there needs to be some kind of interruption because of loading and unloading the work, or that it's out of raw materials or whatever. The plant level, factory or production systems level, this is certainly a possibility. I would say Amazon does this with their shipping centers, where they have a coordinated system moving all its packages around. And at the enterprise level, we would consider that to be the corporate information system. What information are we gathering? How are we able to adjust and control using that information? All right, so you can see they've got it as a 5-level idea of automation, right? And again, all this does is provide us a diagram of what these various levels look like, and how the information flows back and forth. All right, so automation and artificial intelligence. Artificial intelligence, a field of study usually associated with computer science, in which a machine, for example, a computer, is endowed with the cognitive capabilities such as perceiving, reasoning, learning, and remembering. So, areas of application used so far: problem solving and game playing, natural language communication, analyzing large amounts of data and information, planning and strategizing, drawing inferences from incomplete data. Okay, so artificial intelligence has been getting better and better. One thing that we should remember about automation right now is that people are very worried, oh my God, I'm going to lose my job, robots are taking over the world. Right now, any level of automation has traditionally resulted in more human employment not less. In the future, though, as artificial intelligence gets better and better, and robots can repair themselves or can repair each other, then it's going to become a bit of a problem. All right, so an expert system, these are computer programs that contain the technical knowledge of experts from a given field, right? So the examples they give are in botanical science or medical science. In other words, it's a knowledge base, right? And sometimes we have those, for example, in troubleshooting your computer. There are a lot of programs, particularly in Windows, that will lead you through a troubleshooting sequence about why your printer isn't connected properly, or other things of this type, where it helps you to just go through step by step and fix the problem. So it's a knowledge base. It has the general facts, the principles, procedures, and rules of thumb that are used by the same human experts to solve complex problems. Okay, well, that works for me. All of this is going to work together in an algorithm for applying the knowledge to problems, right? So if we were to look at a diagram of it, it would be, I ask a question, hey, I'm having trouble with my printer. Then the computer is going to give me options. Is it a new printer I just installed, or has it been working with the computer? Right? And it's going to keep going down and branching on those decisions until it finds something that is a reasonable approximation of my problem. So they're calling it an inference engine. And we are applying that knowledge base to the facts of our new problem in this application. All right. When we talk about data mining, what we are doing is we are searching data for links that give us more information, or as they say, computational process for analyzing large amounts of data to extract useful information and search for patterns and trends. We have examples here. E-commerce marketing. Identify each customer's purchasing preferences and direct advertising towards those preferences. Right? So this happens to you all the time. When you're looking on the computer, when I was thinking about buying a new car, I did a little research. Oh my dog, I was getting ads for cars for 6 months afterwards. In manufacturing, though, we're analyzing our shop floor data to indicate operating performance. Hang on a second, somebody is at the door. So sorry for disturbing you. For those of you at home wondering, it was the custodian cleaning the door, which was leading to a bunch of thumps that I mistook for somebody wanting in. All right, so when we're analyzing shop floor data, one of the metrics used is called OEE, or Overall Equipment Effectiveness. This is a kind of way of looking at the utilization of equipment throughout the plant and saying, we're doing pretty good. Our equipment is being used 75% of the time. Now, we should never use that metric in isolation. And I've got something that happened back in the day. Ford had a plant in Pennsylvania. And at that plant, they were making cars, of course, but the only metric that management was being evaluated on was OEE, the Overall Equipment Effectiveness. So what they did was they started running the machines pretty much 100% of the time. They were making parts that they didn't need just so that the equipment would be running and measured as a higher percentage of use. And then they would take those extra parts that they didn't need and they would dump them in the Delaware River that ran right next to the plant. We should always be very careful with our metrics and make sure we understand not only what they're measuring, but we need to think through why we're measuring that and how someone might be able to trick the system into making it look like they're doing a good job, when in fact, as happened at that Ford plant on the Delaware River, they were actually spending a bunch of money and on materials and electricity they didn't need just to make themselves look good. All right, so if we have artificial intelligence, that implies that our machines can learn. I've done some work with neural networks when I was at Ohio University. And my advisor, Dr. Weckman, is a big advocate of using neural networks. Neural networks can be trained to give us operating parameters for various things. I don't want to be super specific here because it really is amazing what is the flexibility of using this. A lot of people don't like neural networks because, like the neural network in your head, it is hard to see in there to see how it is happening. All right, so a computer algorithm able to learn on its own without being taught explicitly, right? A neural network is like that. Once you set it up, you run it and run it and run it, and then you test it to make sure that it can make the correct decisions for given situations. Machines that are capable of learning expand their knowledge base through experience and observations of their environment. So, in other words, the machines are learning much like you learn. You started off with a very small knowledge base when you were born, although some argue that there are instincts that come into play that are very important. And over time, through your experience and your observations of the environment, you learn different things. All right, so we have different ways machines can learn. With supervised learning, in other words, somebody is keeping an eye on the learning. We might think of this class as being supervised learning, right? Y'all could learn this material by reading the book and then but you would miss these wonderful, wonderful insights that I bring in from my experience to the question at hand. We can have reinforced learning. In other words, we make sure that the same lesson is repeated until the machine gets it. And then you can have unsupervised learning. You just let it go wild and it will eventually learn through experience and observation. So, when we have supervised learning, we give sample inputs and outputs presented to the computer, and it learns to recognize the relationships that are involved. In reinforced learning, we get positive and negative feedback as it's learning from its observations. And with unsupervised, we just leave the computer to its own thing to figure out structure and knowledge from its observations. All right, so we saw this diagram before where we have a machine operating under a program control. There's no human participation, right? So we have our power that feeds into the program of instructions, that feeds into the control system. There's feedback back and forth with the process. And then we have the process output. Strangely enough, we don't seem to have a process input in this schema. When we have artificial intelligence applied to this kind of a process, then things from the environment are feeding into the knowledge base. It goes through an algorithm, right? We're assuming there's reasoning power that feeds into both of these. Which goes back and forth with the problem to give us an output or a solution, as it were. All right, so how can we use this kind of artificial intelligence application in manufacturing? Well, we can have computer-aided process planning. This could be at a very low level, like we just set up an Excel sheet where we have links back and forth that allow us to input a very few things, and then the machine gives us an answer. Hey, you need to build 12 of these part X, you need 3 part Ys, and so on down the line. We can have computer numeric control part programming to run machines. We can have robot programming. We can have robots interacting with humans. We can have production planning and control, diagnosis of machine malfunctions, and routing of autonomous material transport vehicles. Although usually these are called AGVs, or automated guided vehicles. So we might have smart manufacturing and smart factories, Industry 4.0. They are referring to people who believe that our smart manufacturing, where we're using computers to aid us in manufacturing, is going to be the fourth industrial revolution, and eventually identified as that. So the industrial revolutions that they're seeing, that they are identifying so far, the first one, you had the steam engine, textile machines, machine tools, mechanization, and the factory system. And they're identifying this as happening in 1760 to 1830. Although there are elements in there that go even earlier. The second industrial revolution, they characterize with mass production, electrification, assembly lines, steel making, mechanization from 1830 to 1900. Again, some parts of that had started much, much earlier than that. The third industrial revolution, they say the internal combustion engine, computers, automation, radio and TV, and the internet from 1900 to 2010. Okay, whatever, man. Arguably, some of these ideas, again, were invented before 1900. And I hear Otto and Rudolf Diesel turning over in their graves right now. The fourth industrial revolution, they're saying smart manufacturing, cyber physical systems, artificial intelligence, smart machines, and the Internet of Things. Okay, well, I'm a bit dubious of the hard and fast classifications they're putting on these, while at the same time really loving the advances in the devices that we have to do work in the present day. All right, so our essence of smart manufacturing and Industry 4.0. Manufacturing is defined with a life cycle view that includes not just manufacturing operations, but also product conceptualization and final disposal and/or recycling of the product. All right, I will applaud that. Back in the day when I was a mere slip of a boy going to engineering school, they told us to treat the atmosphere as an inexhaustible resource, that we could dump anything we wanted. Even at the time, I was somewhat suspicious of this viewpoint. Now we try to think all the way from the initial thought for making a product until that product is disposed of, and that is a good thing. Throughout the product life cycle, there is an emphasis on the capture, generation, dissemination, and application of data and information to optimize business performance. Well, that is definitely a necessary thing in today's society. Our modern business and industrial practice means that the cycles are much, much faster than they used to be, and we must continuously be re-evaluated. 3, equipment in the factories comprises intelligent machines, smart robots, and an internet-connected communications network, the Industrial Internet of Things, or IIoT. Okay, well, we're definitely getting more and more closely connected in our business and industry, and there's no denying that. All right, once again, damn it, remember until you die, this is under copyright. All right, I see that I have used up our class time for today. Next Tuesday, as I said, I'm going to work through some problems from chapters 2 and 3 to make sure that we have the essence of how to work those problems down. Thank you very much for watching this video, and when the fields are white with daisies, we'll meet again.